讲那个第4章的后半部哈。Let's come to the second half of chapter 4. So the first topic we'd like to talk about is wave propagation in lossy medium. That is, as wave propagates, its energy will dissipate within the propagation medium. And as a result, the magnitude of the electric and magnetic field shall attenuate. Okay, that is, the field amplitude will become smaller and smaller as it propagates. We have already seen the propagation constant in lossy media. That is, we use gamma to represent the propagation constant. As you can remember, if the propagation medium is lossless, then the propagation constant becomes a purely imaginary number. Okay, here the propagation constant is gamma equals to alpha plus j beta. Alpha is referred as the attenuation constant, beta is the phase constant. So gamma is a complex number. But keep in mind that both alpha and beta are positive real number for ordinary material. Unless you are talking about left-hand material or artificial material, some fancy stuff. Otherwise, the alpha and beta should be positive real number. Okay, so in lossless medium, you have no attenuation. Then the propagation constant is reduced to a pure imaginary number, just the j beta. Therefore, the minus gamma to the square becomes plus beta to the square. And beta to the square equals to omega to the square times mu times epsilon. Then, of course, here we are talking about propagation in lossy medium. So the omega to the square times mu times epsilon term must have the imaginary part. Usually, the most likely case is epsilon E, the effective permittivity. Effective permittivity is a complex number. So the general formation of epsilon E equals to epsilon prime minus j times sigma E over omega. So epsilon prime, the first term, is the ordinary permittivity. Due to what? Due to electric dipole moment. While the conductivity in the medium, that is the sigma E, is the main cause, is the cause for the wave attenuation. 所以这边你看到式子里头那个导电系数我们说电磁波怕水，怕导电系数只要你有导电系数，电磁波就会为什么有导电系数，你电磁波就会衰减？Why wave attenuates when it comes to non-zero conductivity? Because J conduction current J equal to sigma times E. If you have the electrical field intensity and you have conductivity at the same time, it will induce conduction current. The generation of conduction current, of course, requires some energy. So it turns out that if you are propagate in a somewhat conductive medium, then part of the energy of the wave will becomes the energy of your conduction current, okay? And the composition of sigma E is not that simple, okay? Remember that we are talking about advanced electromagnetics, so we need to take into account a more realistic case, take into account more parameters. So sigma E is the effective conductivity, and the effective conductivity comprise two parts. First part is sigma S. S stands for what? 你们猜得到 S 代表什么？代表静态、静电嘛 ，steady field. Okay, so sigma S is the conductivity for static field. While the second term, omega epsilon double prime, is the conductivity due to polarization. Okay. So the composition of the conductivity becomes more complicated as well. So as you can see, the second term is frequency dependent. The second term is frequency dependent. All right. Again, the representation of the field comprises two parts: the amplitude function and the phase function. The phase function here is returned as capital theta. So it's a little bit, and the phase function includes gamma XX minus gamma XX minus gamma YY and minus gamma ZZ. So they are not R, they are gamma. They are the projection of the propagation constant on x-axis, y-axis, and z-axis. Okay, so therefore, the sum of the square of the projections equals to gamma to the square. All right? So the field phi can also be written like this. You have you have product of the three exponential terms, and the index of each exponential terms are complex number as well. So because they are complex number, we can separate them into real part and imaginary part. So the real part is written as delta function of position R. And the imaginary part is J phi of R, also a function of position, of position. 我这个没有改好哈，这个也是伽马，这不是 R， 这是伽马 here. Sorry about that. 这个是 R 没有问题了，这个是 R. Okay, so the real part is pertinent, is related to the attenuation constant alpha. So you can express it in terms of the projection of alpha on x, y, and z axis. And so does the imaginary part. It can be separated into projection of beta on x, y, and z directions times the position. Okay. So the vector propagation constant, by definition, is the minus of the gradient of the phase function. 传播常数是相位函数的梯度的负值So by definition, the propagation constant is the minus of the gradient of the phase constant. So we can substitute capital theta R with delta R and J phi R and perform the gradient operation respectively. Okay, But this is kind of trivial. Yeah. We just simply put it as the summation of course, gamma is, the phase constant is a vector. So it can be written as the summation of its projection in x, y, and z axis. And so there's attenuation constant and phase constant. Okay. So that's the composition of the propagation constant. Okay, now let's do some interesting things. Here we do the dot product of gamma by itself. Gamma dot gamma, of course, is gamma to the square. And if you substitute gamma with alpha plus j beta twice in both of them, you end up with the dot product of alpha itself minus the dot product of beta, because of the beta is come with j. Okay, so the product of the square of j equals to -1, and and plus 2 times j alpha dot beta. Okay, so gamma can be regrouped as this. And as you can see here, as I mentioned at the first slide, that alpha and beta are positive real number. So the alpha to the squared minus beta to the squared term is real. It can be regarded as the real power of gamma to the square. And the third term, which comes with j in the front, and as you can imagine, it's the imaginary part of gamma to the square. So, what are the implications of this? If the dot product of alpha and beta are non-zero, then this term, a non-zero term for this suggests we will have attenuation, we will have loss in the medium, okay, for this term. So because the requirement for lossy media is that the imaginary power of gamma to the square is non-zero, so we can think of what are the conditions to achieve lossless medium. So to achieve lossless medium, lossless propagation, then we shall have alpha, the dot beta equals to 0. This can be accomplished with the two conditions。所以上一页我们上一页讲到你伽马的那个相位常数的不是传播常数的平方值，它的实部，它的虚部代表的是耗损的部分所以我们这边看一下，假如你要让达到无耗损的传播的话，有什么样的条件必须要满足所以也就是2阿尔法打贝塔必须要等于0嘛那这边其实有一件蛮好玩的事情，你可以看得到，一个是阿尔法等于0，这个很简单嘛假如你没有那个 attenuation constant 的话，当然没有 attenuation。那刚刚 so if alpha equals to 0 this term goes to 0 as well, and in the previous slide, the alpha to the square minus beta to the square term is reduced to just minus beta to the square because alpha equals to 0. Okay, so it becomes the lossless case. So the ordinary case is have 0. The ordinary case for achieving lossless propagation is to setting the alpha, the attenuation constant, as 0. Okay, you already know that it's not surprising. The second case is more interesting, and We probably won't be able to discuss this today, but in Chapter 5, when it comes to the so-called evanescent wave or surface wave, we will come into these situations. They are more interesting. The other criteria, the other condition that you can achieve the dot product of alpha and beta equals to 0 is alpha, the vector alpha and the vector beta are perpendicular to each other, are orthogonal to each other. If they are orthogonal to each other, then the dot product term becomes 0 as well. So have you ever come to across this kind of phenomenon? 有遇过这种状况吗？可能没有哈。它这个叫做 evanescent wave 啦，一个比较常见的例子叫 evanescent wave。何老师啊 ，evanescent wave 跟 surface wave 一不一样？我自己在想这件事的时候，有点不是很有把握。什么是 evanescent wave 啊？哦 ，sorry， 你波打进来，我好像太暴力了。OK， 今天不太能够控制我的肌肉能力。我昨天早上去打 AZ 第二剂，听人家说 AZ 第二剂不会有反应哦。就昨天晚上9点开始打摆子哦，觉得就是说天哪，今天是蛮冷，昨天是蛮冷的，但有那么冷吗？哈，就盖了2层被子哦 ，OK。后来熬到半夜3点的时候，觉得好像就退烧了哈 ，OK。不过可能 ，OK。So supposing this is a conductive material, this is air. If a wave coming in this direction, okay, as we know that the wave energy cannot penetrating into a conductor, but in actual case, the E field of incident wave can goes into the conductor a little bit, just a little bit, okay, just a little bit. So your attenuation constant is oriented in this way. And you may have, but you still have phase variation on the surface of the interface. Okay, so for this case, you may have a field goes along in this direction. So they are perpendicular to each other. Okay? So this part is called evanescent wave. What is the meaning of evanescent? Dies out very quickly. 很快就死掉了，很快就没了，很快就消失的。And this part is, as far as I can remember, is referred as the surface wave. But I'm not so sure about this. Yeah, okay. So that's a special case. That's a special case that you have different direction for your propagation constant and for your phase constant and the attenuation constant, all right? So in lossy media, alpha and beta don't have to be in the same direction, okay? Even though they are in the same direction most of the time, but they are not necessarily in the same direction. So let's check up the wave equation for electrical field again. So that's the wave equation in medium. And what is the implication of this? Divergence of E equals to 0. This means the median is source-free, no charge, no charge. If this is non-zero, then you have electrical charge in that place. So if you substitute E field representation with the E sub 0 times exponential minus gamma dot R. Okay, so the first one is your propagation constant. The second one, R, is your position description. Okay, so the phase is dependent of the inner product of the two. Okay, and it becomes scalar. Okay, gamma is a vector. R, the position vector, is a vector, but the dot product of the two becomes a scalar. Okay, and of course you need to identify this is position vector R, not gamma again. Okay, so the two are different. All right, and if you substitute the E field representation of this within the divergence of E, you end up with this result. The first term is the divergence of E sub 0, which is 0, because E sub 0 is a constant. E sub 0 is the constant amplitude. Okay, so you have no spatial derivative in the space. The second, so let's end up with the second term must go to 0. So what is the implication of this result? 这个结果所指的物理意涵是什么？电场的振动方向跟传播方向必须要正交，对不对？好 ，because the dot product of propagation constant and the E field equals to 0, which suggests the propagation direction and the vibrating direction of the E field must equal to 0. That is, the projection of gamma on XYZ axis, and the projection of E on XYZ axis, the dot product of the two must equal to 0. So, as a consequence, 它的结果是什么？ Propagation constant direction is perpendicular to E field in Lossless Median 2. 在耗损材料中传播的波也是 TEM wave。假如你没有边界的话，假如在没有边界条件束缚的状况之下 ，free space 那个耗损材料中传播的也会是 TEM wave。OK。Now let's go back to the Faraday's law, that is the curl of E equals to the minus J omega mu H. Okay, we already learned from the last lecture that the H direction and the H field direction, E field direction, and the wave propagation direction are perpendicular to each other. So E cross H end up with the wave propagation direction. H cross K or H cross beta or H cross gamma here. Okay, H cross gamma here. You will end up with E direction, and so on and so forth. All right, so the Faraday's law can be substituted with this, so that the H magnetic field representation can be found as gamma cross E divided by J omega mu. J omega mu. Okay. And in this last case, the gamma can be substituted with minus J beta. And here we assume alpha beta in gamma are in the same direction. So this can be satisfied for most material. And here is the dot product of gamma by itself. So of course we know that gamma equals gamma to the square, and everything within has this relationship. So gamma is the square root of minus omega to the square times mu times epsilon e. And you can rewrite the H representation here by substituting gamma with gamma hat. That's the unit vector of gamma times gamma itself, the magnitude of gamma, cross E. Okay? So what is the purpose of doing this? The purpose of doing this is try to, because this is the unit vector, so the magnitude of this is 1. This is the E field representation, this is the H field representation. So everything else, that is gamma over j omega mu, stands for what? Stands for the ratio of E over H or H over E, okay? So, well, it stands for H over E, all right? So if you substitute gamma with this representation and compare with the denominator, you found the omega to the square term goes away, the j term goes away as well, and you end up with epsilon effective permittivity over mu. So it's actually the inverse of what? Of your intrinsic impedance, right? So this is the inverse of intrinsic impedance, which is also the ratio of H field over E field. Is this a real number or a complex number? A complex number. Okay, so the absolute value of this is the ratio of H field magnitude over E field magnitude. 好，从绝对值来讲，它代表的是磁场跟电场的比值。但因为这个是 complex number 嘛，好，所以在 Lossless Median 里头一个有趣的事情，跟 Lossless Median 里头有一个不一样的事情，在 Lossless Median 里头你的 Intrinsic Impedance 是个 real number， 所以它也告诉你电场跟磁场是同步的，有没有？好，在没有耗损的材料里头，电场跟磁场是同步的。在有耗损的材料里头，你的电场磁场比值是一个 complex number， 而 complex number 是有相位的嘛，所以相位这件事告诉你的就是说，电场跟磁场有相位差，电场跟磁场没有同步，在 lossy 的材料里头。好 ，so because epsilon E is a complex number, so the whole thing is a complex number as well, which suggests that the intrinsic impedance of a Lossless Median is a complex number, and it also suggests that the E and H fields are not in phase. There is a phase difference between the two. So now we can define the intrinsic impedance in Lossless Median. That is the square root of mu over epsilon sub E. Epsilon sub E is a complex number. Of course, mu can be a complex number as well. What kind of material will have a mu as a complex number? 磁性材料，而且是有耗损的磁性材料。有耗损的磁性材料也会有但我们比较少碰到有耗损的磁性材料吧，所以 for simplicity 让大家问题稍微简化一点所以我们这边并没有把mu用 complex number 来 来去代入了哈。我们只有讨论，比较常遇到的是 epsilon 是 complex number 的情形哈，所以我们把它用 mu 的部分就用单纯的 mu 了哈。OK. Alright, so as we defined previously, according to our previous definition, H equals to this, and this thing, gamma over j omega mu, is the inverse of intrinsic impedance. So by introduce the intrinsic impedance eta c, the relationship between H and E field can be written like this, which is quite similar to the lossless case. Where intrinsic impedance eta sub 0 is a real number. It's a real number. Here, eta c is a complex number, right? So here is the representation of H field due to an E field in the x direction. 好，这边我们可能要看前面几页的那个结果哈，因为我们等于把这个东西我看拉得比较远了哈，拉得比较远，或者说我们在这边再多看一下哈，所以这代表什么？The H field representation here tells you that the vibration direction of the magnetic field intensity is in the y direction. What is the propagation direction of the field? The propagation direction of the field can be seen from here. Can be seen from here. And let's see. So here is the propagation constant gamma, which equals to. 好 ，so here is another typo. 这边请你改一下，这是 gamma 不是 r， 这是 gamma 不是 r。Alpha plus j beta is gamma and equals to this. And the direction of gamma can be found by taking the gradient of the phase function. Okay? So we are taking the phase function is everything here on the exponential. So if you taking the gradient of this, you end up with sine theta I in the x direction and the cosine theta I in the z direction. And here is your propagation constant, gamma. 好，所以这边有没有看懂？这是磁场的表示式，磁场的表示式有它的 amplitude， 当然这边的 amplitude 是一个定值，一个 constant。那它的相位部分是 exponential blah blah blah， 好，所以那个 blah 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 exponential blah 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 的东西是你的相位函数，相位函数的 gradient 的赋值，相位函数的 gradient 的赋值 by definition 是你的相位常数啊。所以我们把这个表示式抓出来，其实就可以找到你的传播方向，你的传播方向 ，OK？ And according to this relationship, you can find out the alpha and beta in vector form. Alpha and beta. Here you just have the magnitude of alpha and beta. Okay, we know that alpha and beta are positive real number, but the more complete description of alpha and beta are vectors. So you need to include not only the magnitude, but the direction as well. Okay, so as you can see here, alpha and beta are in the same direction, and they have only projection on x direction and z direction, no projection on the y direction. 好，所以它是一个在 xz plane 上面传播的波，磁场的振动方向在 y 方向，啊，磁场的振动方向在 y 方向，啊。那其实你可以从这个找出电场，啊，所以这一页其实告诉我们怎么样找到电场的表示式，啊，那事实上也就是你的 gamma cross h。gamma cross h 就可以让你得到1了the cross product of gamma and h times times the intrinsic impedance will give you the E field representation. So here we have, this is the propagation constant. This is the unit vector of the propagation constant, okay? So this part is the magnitude. This part is only the description of direction, all right? And we begin with this relationship and do the cross product of gamma on both sides. So you have gamma cross H, gamma cross E. We use the unit gamma hat, the unit vector of gamma. And because of the vector identity, okay, so this is valid for any vector. You do the cross and cross again, you will end up to the reverse direction of E field itself. So because of this, this part can be substituted with minus E, simply with minus E, okay? Then we only need to carry out this cross product. And we can substitute gamma hat like this, sin theta I, cosine theta I, and H has only the HY term. So do the cross product like this, you end up with this result, okay? So you should go over the slides, go over the equation, okay, at home for those slides, okay? So the result we'd like to derive is this part, okay? That's the relationship between E and H field. Okay, you can. So the first last thing we'd like to discuss about wave propagation in lossy media is the energy, from the energy perspective. We try to express the pointing vector in Phasor form. So the very first equation is the pointing vector. It is expressed as E cross complex conjugate of H. They are all in Phasor form, and we know that they are sinusoidal signal because of Phasor form. They are sinusoidal signal. So you substitute the H conjugate with H expression and taking the conjugate. So here you have gamma star, E star, J omega mu star. J omega mu star is just minus J omega mu, right? Yeah. And it can go from here to here, okay? Why? Because gamma star can be divided into so we can separate the two. The second half combined with this becomes eta C star, okay? And we can use the vector identity over here. Here you see the triple product, E cross gamma cross E conjugate. And you can identify E as A, gamma hat as B, and E conjugate as C, and substitute it into the two terms. One will go away, the other term will end up with this. That should be the first term. I guess that should be the first term. Okay? That would be the gamma hat, E dot E complex conjugate over 2 times eta C complex conjugate. What is the implication of this? This tells you the direction of energy, the direction of propagating energy. It's in the gamma direction. 能量传播的方向还是跟相位常数决定。所以这是 pointing vector 嘛 ，pointing vector 指的是能量，而且 pointing vector 是一个向量嘛，所以它告诉你的是那个 gamma hat 告诉你的是能量传播的方向，其他的东西告诉你是传播能量的大小。所以 E dot E conjugate, even though that E is a complex number, but the E dot E conjugate is a real number. Okay? And you can identify that it's like very similar to the 2分之一 v 平方 r 嘛。这个是能量的表示式。那这个是能量密度啦 ，OK？ 这是能量密度，因为是电场，所以它还缺了一个 m。所以这个是本质阻抗嘛，这是电场，电场的平方除上本质阻抗，所以它代表的是能量密度。你再乘上面积之后就变成能量了 ，OK？ Yeah, I still have a few slides. I'm still a few slides shy of this. Yeah, let me try to finish this before we take a break. So the product of the two, E dot E complex conjugate, originally you should have exponential minus gamma hat dot r times exponential. When you're taking the complex conjugate, you kind of change the sign of your imaginary part, right? So gamma is alpha plus j beta 嘛，所以你把它相乘的时候，那个 beta 的部分就 cancel 掉了，So you do the dot product of a vector and its complex conjugate, you're just taking out the real part. The imaginary part is cancelled. The imaginary part is cancelled. So you substitute an E-field representation with propagation constant gamma. You end up with the exponential minus 2 times alpha, the attenuation constant. Okay, so as you can see, the further the wave propagates, the smaller the amplitude of this becomes. Okay? The exponential is the index of the exponential is a real number. Alpha is a positive real number. So the bigger the propagation distance is, the smaller these terms become. So it's valid for a description for attenuating wave. The rest of the things are, we have seen this before. And here is the general representation for mu and epsilon. Okay, so as I mentioned earlier, mu can be a complex number just like the epsilon. Epsilon is a complex number as well. While the epsilon E double prime term is comprise the conductivity of the median over omega. And for most material, for most non-magnetic material, the mu double prime term is 0. Okay, so the alpha and beta for the propagation constant. This is the analytical solution of alpha and beta. 所以右上角其实是完整的解啦，完整的解，你只要把 mu 跟 epsilon 带进去的话，它会是右上角那个完整解。那 well, this kind of scary, and you probably don't want to remember alpha and beta form in analytical solution. So what we really need to do is taking two extreme example to see what things become for this alpha and beta terms, and remember the physical interpretation of the things. So first thing I would like to examine is, suppose we have good dielectric. In good dielectric, where you have conduction current, 你会不会有传导电流？就算有，也不会太多。只要你的材质是一个好的 dielectric， 是一个算是好的绝缘体的话，你的 conduction current 应该要少。但是因为电场变大变小 ，due to the variation in electrical field, you shall have displacement current in your dielectric. So JD, D stands for displacement current, should be much larger than JC. So the ratio of JC over JD is much smaller than 1, which means this is a very small number. Then you can use the binomial expansion term. There was a typo, okay, on the slide, on the printout. Originally times n, it should be 1 plus x to the n. 我这边有打错啊，讲义上面有打错啊，你修正一下。So if you apply this condition, you end up with these two terms. And it turns out that beta is the dominant term for good conductors, for good dielectrics. Your phase constant is much bigger than your attenuation constant, even though that the attenuation constant cannot be neglected, okay, for lossy medium. Okay. Alright, so the first case is that the displacement, the dielectric is not perfect, but it's good in general, so you need to account for signal attenuation because of non-zero alpha. The second situation is here. If you have good conductors, JC is much greater than JD. You have this term is greater than 1, as you can imagine. You end up with alpha equal to beta like this. Alpha equals to beta like this. So if alpha and beta are equal, then you end up with a gamma. So the phase of this thing is 45 degrees. So this is an interesting fact, that the propagation constant, the phase of the propagation constant is 45 degrees for conductors. Tell you one truth. Can you tell a metal surface by looking at it? You can do that, right? Why? Because the reflection of metal surface is special. How special? I don't know. But this is due to this. 为什么金属表面看起来会有特别的光泽？因为它的反射受到这个影响。受到这个影响，它的反射会受到它的反射系数会受到那个45度的那个相位变动的影响。好，我还没讲完 ，OK， 但是我快要站到下一堂课了 ，OK。Skin depths, I'll continue in the next lecture. 我们等一下再讲好了，等一下再讲，先到这边。我们可能